Now let's talk about light and the mirror equation. Now I want you to pay attention because we're going to use this formula over and over again in this unit. Now, suppose I have a mirror. Your object is always in front of the mirror, no matter which direction your mirror is facing. So just remember that, because you can't see anything in a mirror if it's behind the mirror, can you? Now the image is what is produced. It's what you see in the mirror. Now the image can be real or it can be virtual. A real image occurs in front of the mirror, or you can say a real image can be reflected on a screen or a surface of some sort. While a virtual image is one that's behind the mirror, and you can't project a virtual image on a screen of any sort. Now the last thing you need to know is the principal axis. The principal axis is just the central axis, and it's what we use as a reference for our object and image. So the principal axis is always going to be this horizontal line that runs through the object and the image. Now there are three kinds of mirrors. The first is a flat or a plane mirror. Now for a flat or plane mirror, the image is always going to be virtual, so it's always going to be behind. Imagine you're standing in your bathroom and your mirror is against the wall. You appear to be behind the mirror, even though you're not, in your yard or in your kitchen or wherever. The image appears to be behind wherever your mirror is. Now the image also has left to right reversal. You raise your right hand, your image raises its left hand. Now the image distance and the object distance are always the same on a flat plane mirror. And the height of the object is always the same as the height of the image. So remember, the height of the object is HO, the height of the image is HI. We're using O for object, and I always stands for image. H stands for height, and we're going to use S for distance to the mirror, or distance to the mirror for either the object or the image. Now, what if we have a curved mirror? Imagine you have this curved mirror. In the center of it, you have the center of curvature. And halfway between the center of curvature and the edge, any edge, is the focus. So the radius of curvature R is always going to be the distance from C to the mirror itself. And the focal point is always going to be halfway between R and the mirror. Now the focal point F is where the light rays come together. If I were to throw in light rays through here, we're going to do this in a little bit. And so remember, the radius of curvature is always twice the focus. Now let's talk about concave mirrors. We use these when we need to magnify an image. We also call these converging mirrors because the light rays come in and converge on a point, and that point is the focus. Now the image is the position where the rays come together and the image is formed. The image will also be different sizes. For a concave mirror, the image can be real or it can be virtual. So you can project it on a screen or not project it on a screen. Convex mirrors are different. These are called diverging mirrors because light rays come in and then they diverge from a focus right here. The focal point and the center of curvature are always on the opposite side of the mirror where you're not standing. So the focal length is negative. You know you're dealing with a convex mirror when I tell you the focus is negative 20 centimeters. That negative sign right there tells me the focus is on the wrong side of the mirror, on the opposite side of the mirror, and we're dealing with a convex mirror. Now, images are always virtual, upright, and reduced. Why do we use these? Store mirrors. You know how they can kind of see around the corners? If you look at your passenger mirror, it says objects are closer than they appear. This is a convex mirror. Now, sometimes in big schools, they'll have these sorts of mirrors at the intersections of busy hallways. Now, ray diagrams are always interesting. We use the same rays as a concave mirror, and we're going to get into what those are. Except whenever you have rays behind the mirror, we draw those as dotted lines because the rays aren't really there. So remember, the focus is behind the mirror and it's negative, and the images are always virtual, upright, and reduced. Now let's talk about the mirror equation. It relates the focus to the object distance and the image distance. And it's very straightforward. 1 over F is 1 over SO plus 1 over SI. Now I get lazy, and a lot of times I just write it 1 over F is 1 over O plus 1 over I. Where SO is the object distance, O is object, I is the image distance, and F is, of course, a focal length. You notice it doesn't matter whether it's convex or concave mirrors. Just make sure you put in the positive or negative focus. Now let's talk about the magnification. This is how large or how small the image is with respect to the object height. So if I have an object that has some height, HO, and then I have an image back here, HI, obviously the magnification is going to be the image height divided by the object height. Now it turns out we can also write it as minus the image distance divided by the object distance. Now, sign conventions. Your object is always positive. Please, doesn't do you good to stick an object behind the mirror. If the image is positive, it's real and it's going to be in front of the mirror. If the image is negative, it's virtual and behind the mirror. If the height is positive, then it's upright, and that just means it's above the principal axis. While if the height is negative, it's just hanging upside down, and the magnification is going to be negative. Remember, F is positive for converging lenses and negative for diverging lenses. Finally, for the magnification, and think about this, if the absolute value of the magnification is greater than 1, then the image is larger than the object. That kind of makes sense. If the absolute value of the magnification is less than 1, then the image is smaller than the object. Well, if the magnification is equal to 1, then that just tells you that the image and the object are the exact same size. Now, whenever you have a magnification that's less than 0, that is, it's negative, it's inverted. It just means it's upside down, and you're going to get a negative height. Remember, concave, focus is positive, convex, focus is negative.